How far can a single pixel camera go? Solving vision tasks using photoreceptors and computationally designed visual morphology. The status quo in solving computer vision tasks is to use a high-resolution camera and intuitively design its position on the agent. In nature, on the other hand, there are various examples of extremely simple, low-resolution eyes that still allow animals to exhibit diverse behaviors. In addition, the design of these eyes is optimized for a specific animal's body, behavior, and environment it lives in. In this work, we explore how far can simple visual sensors go in computer vision. We replace the standard camera with a simple photoreceptor. It can be seen as a camera with only a single pixel. We then show that simple photoreceptors are effective visual sensors and can solve different vision tasks such as vision-based navigation or continuous control. We show that the design of these sensors plays a crucial role in their effectiveness. And finally, we develop a computational design optimization method to find well-performing designs. First, we demonstrate the effectiveness of photoreceptors in visual navigation. The task here is to navigate to the target object placed in a new environment using a visual signal as an input. Here you can see an example of an episode solved with a camera. We use scans of real-world apartments to train and test the agents. Now, instead of a high-resolution camera, we equip the agent with only a few photoreceptors. We find it can successfully solve the task while relying on the low-dimensional visual signal. We compare the performance of photoreceptor agent with two control baselines. First is an intelligent blind agent that doesn't have any visual signal. It learns the structure and biases of the task and training data and serves as a lower bound. Second is a camera agent that uses a high-resolution camera sensor. We find that even a handful of photoreceptors can be enough to solve this visual navigation task meaningfully well. We also explore the effectiveness of photoreceptors in the real world and deploy the control policy trained in simulation directly onto a real robot. We find that the agent is able to successfully explore the scene, detect the target, and navigate towards it. While the agent doesn't succeed in all episodes, it shows overall not trivial generalization. We also evaluate photoreceptors in continuous control tasks in DeepMind Control Suite. We use tasks for 3 different agents, and similar to visual navigation, we compare photoreceptor agents shown in blue with the intelligent blind in gray and the camera in red. The x-axis shows the number of used photoreceptors. We find that in most cases, just as few as 4 or 8 photoreceptors can be enough to solve these tasks meaningfully well. We show an example of the walk task solved using only 4 photoreceptors. The left image shows the placement of those photoreceptors. The middle plots visualize the corresponding observation, original RGB values on the top and the luminance on the bottom for easier interpretation. The right image shows the side view not seen by the agent. We find that the agent can successfully control its body only based on the low-dimensional visual signal. We now study the role of the design in the effectiveness of photoreceptors. In this work by design, we refer to the position, orientation, and field of view of visual sensor. But the same framework can be applied to model other sensor designs, for example those found in nature. We show that these design parameters play a crucial role in achieving good performance. The plot shows the performance of different designs for each task and the number of sensors. We find that the performance varies drastically across different designs. This is reminiscent of the ecological visual theory stating that biological vision is specialized to the agent's ecological context. If you are interested in more discussion on perceptual and mechanical morphology and their role in intelligence, you can see the CVPR 2024 tutorial on the computational design. This observation signifies the importance of having a computational design optimization method that finds designs that maximize the downstream objective for a given agent, environment, and task. We develop the following optimization method. First, let's consider standard reinforcement learning with policy gradient. The policy pi gets observations from the simulator, outputs control actions, and so on. After the episode ends, we compute the reward and use it to improve the policy. Now, our observation action loop, and therefore the final reward, depends on the choice of the sensor design. To optimize the design, we model it as a design action sampled by a different design policy. We then use the same reward function to jointly optimize both the control and design policy. We then apply this optimization method to all considered tasks. For each task, we show the performance of the initial random design on the x-axis and the performance of the final computational design on the y-axis. In this case, the design optimization improves the performance as the point lies above the diagonal. Overall, we find that the final computational designs outperform random initializations in most cases. In this work, we show that simple photoreceptors can be effective visual sensors, and their design is essential to achieve good performance. Finally, we develop an optimization method that finds well-performing designs. For more results and analysis, see our project page and the paper. Finally, this direction, inspired by the diversity, simplicity, and specialization of natural vision, prompts us to rethink how we can make effective yet simple computer vision systems, especially for unusual and intuitive applications.